Hi again, Tibra.
Hi, how are you?
I'm good.
All right, awesome.
So
Uh,
your exam went well?
yeah, just quantum mechanics. Yeah, it's quantum mechanics 2. Tomorrow I have quantum mechanics 3. So,
Right.
yeah, this was a large class, so many students were asking a lot of questions. But it went okay. So let me share the screen.
Yes, you can start sharing the screen and then we'll just start in a few moments.
Sure, yeah, no rush. How are things in Pakistan? Everything's good?
Yeah, things are stable. We recently just had the monsoon rain, it's getting heavier every passing year. So like there are cloud bursts and there was slight flooding.
Okay,
Yeah, so there were
yeah.
some catastrophes like some one car, with a family in it. Yeah, so
That's tragic. Yeah, we also had a few days ago, a woman was crossing the street and she fell into a manhole in
oh
the water, and then it took 2 days to retrieve her body. So it's very tragic. These things happen in our part of the world.
yeah, so
Um,
I mean, there are more of internal problems and not many external problems. So in Pakistan, like there more of like we need to pay attention to the climate change and we need to work for
yeah,
global
mm,
warming and and then I'm hearing that we the province of KPK,
mm,
like they are, I guess, protesting that because our own army tries to fight the militants hiding there.
mm,
So, but in that, I guess some innocent citizens are also killed. So
yeah,
these are so like in Pakistan, like there are few provinces who are always crying that we don't get our rights. So that is a problem.
mm. Yeah. We're having problems with minorities. They're being targeted, and the government is not really doing much. So it's very disturbing.
In fact, I wanted to ask that, but I guess like Hasina has returned and she is being tried.
No. Hasina is in exile in India.
Okay,
She had, yeah, no, she is being tried in absentia, but no, she's,
okay,
I don't think India is planning to give her up anytime soon.
right,
So
right.
India is not friends with the current government. So, for example, India has stopped giving Bangladesh's visa except for like medical visas.
Oh,
So, uh, so we can't go to. I mean, I can go probably with because I have a
with your
Western
Canadian,
passport, but yeah. So stuff like that is happening. So it's not, mm, yeah, we don't know what's going to happen. All right. So shall we start or wait a few
yeah,
more
yeah. I
moments?
think we should start. Yes, yes.
Okay. All right. Welcome back. So before the break, I was talking about Wilson lines, and I was just thinking after the lecture, what would be good is to kind of remind people what happens to wave functions when there is a electromagnetic field present. So, so what happens in quantum mechanics? Because we'll need that for Wilson line. So the behavior, say, of wave functions when a background gauge field is present. So for simplicity, I'm just going to take the 3-vector potential. So as you know, the 4-vector potential has a 0th component, which is the scalar potential, and then the vector potential. So we are just going to say this is 0 for now and just work with this. And if you remember, when we write down the Hamiltonian for a charged particle, we basically replace what was the momentum operator by something like this. So this is what we do in the Hamiltonian. And of course, the Hamiltonian is not gauge invariant. However, the Schrodinger equation is gauge invariant. That means that under a gauge transformation, so under the gauge transformation, A changes, so the Hamiltonian will change, but the psi will change as well in a way such that this equation remains invariant. So let's imagine that we have done a gauge transformation. So we have done a gauge transformation. So suppose that we have gone from, say, A to A tilde, where A tilde is the old gauge minus the gradient of some scalar function, lambda. And then the wave function, which I'm writing as alpha, will go up, will change in some manner. So we want to find how this thing is related to this thing. Now we want physical quantities to remain invariant. So we want, say, the expectation value of the position operator to remain invariant. Now the position operator does not depend on A. And therefore, we can say the position operator after the gauge transformation should satisfy this. So that's hint number 1. It tells us that anyway, we'll see how this pans out. And then the momentum operator, on the other hand, if you take the kinematic momentum, so the kinematical momentum and the canonical momentum are different. So the kinematical momentum in terms of the canonical momentum is going to be this. And of course, what we measure is the kinematic momentum, and therefore, this should be invariant under gauge transformation. So here, Q should be, A should be replaced by A tilde. But we see that A tilde, the new gauge field is related to the old gauge field. So I probably wanted a plus sign. It's kind of the same thing, but through the gradient of the scalar field lambda. So now recall that the momentum operator, this was given by minus I h bar delta, right? Because we must have xi pj is equal to I h bar del ij. We are of course taking h bar to be 1. So for that, this has to be true. So now what if you write this thing, we see that this is going to be alpha p minus qa alpha. This will be some alpha, some transformation which we're writing g dagger. And then here we'll have P minus Q A minus Q, the gradient of lambda. And then we will have this transformation G times alpha. So now we use the fact that P is this thing, and we have to have these two things to be equal. So that means that G has to be a function of X, so that when the derivative operator acts on it, it creates exactly this term, or it creates something that cancels this term. Because P has a derivative operator in it, so that when P acts on this, it gives rise to a term that cancels this and gets us back here, right? So if we just play around a little bit, we can show that this is going to be nothing but exponential of I Q lambda, which is a function of X, right? So if we choose our transformation, so if our wave function changes by this, this element, which is, of course, we now recognize it to be an element of the gauge group U1, then we see that these things are true. Okay? So the takeaway from this is that under a gauge transformation, the wave function changes by a factor where this is the gauge function. Okay? Right? So is that clear? This is kind of the rehashing the Bohm-Aharonov argument. I mean, we need this to kind of work out the Bohm-Aharonov-Bohm effect, for example. But this is the standard thing that we do when we're doing quantum mechanics of a charged particle. Okay. So are there any questions?
Yes, the participants can ask in the chat also. So if you have any question, you can type.
Okay. So one should be familiar with this sort of argument from one's advanced quantum mechanics course.
Yeah.
But if you are not, there is a good resource I can give you. So the resource that I would suggest in case you want to brush up your quantum mechanics with charged particles is the book by Sakurai. And of course, after Sakurai died, Neopolitano did some editions, are very nice editions. And I have the physical copy of the second edition, but the third edition has a lot more new problems. So, and the part about, how quantum particles behave in the presence of an electromagnetic field is really superb. So I highly suggest that you read that. Okay, so we were talking before the break about Wilson lines or Wilson loops. And according to Wilson, in non-abelian gauge theory, the fundamental gauge invariant quantities are given by this very strange looking thing, which is the trace of the path order. This is a path ordering operator of the exponential of I of Q over some closed path A mu of dx mu. Right, where A mu is the gauge field So A mu contracted with the generators of my gauge Lie algebra gives me the gauge field. And this does not look very gauge invariant at the moment because it's expressed in terms of A. But the fact that, we can, this gauge invariant quantity is an example. There are other gauge invariant quantities. There could be double trace, more than one objects can be used. We can write this in terms of a surface integral with f mu nu. And I guess this should be an area integral. This is gauge invariant, right? This is gauge covariant, but because of the trace, this becomes gauge invariant. Okay. So now, suppose our gauge group is UN, but we have a gauge field configuration, which is just the, it's in the diagonal. So it has the form of U1 cross U1 cross dot 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 U1. So there are n U1 factors. Okay. So in that case, our Wilson loop becomes abelian because all these A's will now commute, and we can write it without bothering about the path, the trace or the path. I guess there will be still a sum, the path ordering, right? So there will be still a sum. Yeah. Now, it's a very interesting thing is that if we have a zero gauge field strength, then of course it means that physically there is no gauge field. And in flat space, this means that the gauge field A mu doesn't have any physics in it. But that is not the case when our space has a loop in it. And remember that we are dealing with a space which has a circular direction. So if you find this a little bit confusing, the place to look for is to go and look at Bohm-Aharonov effect. If you think of Bohm-Aharonov effect, we have some electromagnetic flux lines going through along the z direction. And in the region around the magnetic flux line, B is 0. But in this region, A is not 0. And if we take a charged particle and move it around this loop, even though the charged particle never interacts with the magnetic field, because the magnetic field is at the center is non-zero, but the region in which the charged particle is being moved around, the magnetic field is 0. Because A is non-zero, the charged particle picks up a phase. So in our case, what we will do is that we will choose f mu nu to be 0, but we will choose some gauge field which is non-zero, but it gives rise to 0 gauge field. Such gauge field configurations are known as flat connections. Okay, so we talked about gauge field. We talked about how particles change in the presence of gauge field. But why is it relevant for string theory? Right now we come to string theory. The thing is that in string theory, when we have an open string, one can add at the end of open string some wave functions, some non-dynamical wave functions, charges called Chan pattern factors. This is just a degree of freedom one has in open strings. They have no dynamic, so the Chan pattern factor Hamiltonian is 0. So they're just there. Now, for strings which are oriented, meaning that their world sheet, is a cylinder, there are the types of strings which are non-oriented, where the world sheet is kind of it's a Mobius band. We won't get into that. So for oriented strings, the Chan pattern factors take value in the group UN. So suppose that we have an open string and its wave function is given by some k, is given by some, and it'll have some momentum or something, some other quantum number. But the end, they will have I and j. And this I and j will take value in the fundamental representation. If I takes value in the fundamental representation of UN, this is how I write, then j will take its value in the anti-fundamental representation, n bar of UN, right? And so we sum over I and j, and there are these wave functions, lambda ij. These are arbitrary numbers. And so what we have here, if you look at a string, on one end, we have a charge transforming in the fundamental representation of n, and at the other end of UN, and at the other end, we have an anti-fundamental representation. So you may or may not know that if I take the cross tensor product of a fundamental or anti-fundamental representation, this gives rise to the adjoint representation. Okay. And the gauge fields A mu of A, they are always in the adjoint representation of the gauge group. In this case, it's UN. So thus we see that by adding Chan pattern factors to the end of open strings, the open strings now carry, they are part of the gauge. They are in the adjoint representation of UN. Okay. So I don't know how familiar you are with this. I wanted to use a different thing, but this is a very famous and important way. In group theory, it's one of the ways of building the adjoint representation. You take a fundamental and an anti-fundamental way. And one way of looking at it is that a fundamental representation of UN is n-dimensional, and the adjoint is n squared, right? So it matches up. This is n-dimensional, this is n-dimensional. So if you multiply this, you get n squared dimensional, which is exactly the dimension of the adjoint representation. Okay, so this means that we have n squared of these gauge fields. Okay. So now what we are going to do is that we are going to say that, okay, we are just going to take we are going to take a flat connection. So that means that we are going to take A25 in such a way that it will give rise to F mu nu equals to 0. But the A25 itself is not going to be 0. It's going to have the form where this is going to be minus I lambda inverse del lambda del x 25. Okay, what is this? So what is this lambda inverse or lambda? This lambda is going to be an n by n matrix whose diagonal elements are non-zero. And the diagonal elements are going to be E, okay. Let me take a step back and just one second. Oh yeah, okay, sorry. Yeah, sorry, it's because I'm having to introduce so many backgrounds, I'm getting a little bit mixed up. So, okay, let's leave this story here and come back to what we were doing. We were doing T duality on a of open string in the background of a circle. So let's go back there, and we'll come back then to the adjoint representation. But if I did a T duality with an open string on open string, so under T duality, the x25, the left moving part, remains as it is, but the right moving part picks up a minus sign. This is similar, this is identical to what we said in terms of alpha. So if I take an open string solution, which is x mu z z bar x mu z plus x mu z bar. So this is an open string solution. How do we know this? Well, we can explicitly write this as x mu z yeah. So we can just like look at the 25th direction. So this is going to be x25 by 2 plus x tilde 25 by 2 minus I alpha prime P25 log of z plus I alpha prime by 2 square root sum over n 1 over n alpha n mu z minus n. So this is the right moving part or left moving, I don't really know which one or the other. And here we are going to have this thing. And now we'll have a minus sign here. So this is prime, x prime of 25. This, of course, then we have minus I alpha P25 log of Z tilde Z bar plus I alpha prime by 2 square root sum over n 1 over n. Now, because it's an open string, these are the same operators, right? So that's the so otherwise there'll be tildes and stuff. So this is the open string. Now under T duality, these are the changes that will happen. So that means that the x25 direction now becomes, in the dual space, the original x25 minus the original x25 z bar. So here we had this thing and this thing adding up. Now there will be subtracting. So this we can now write as x prime mu. Now, this guys go away. We don't have to write mu, we can write 25. And then we are going to have minus I alpha prime P25 log of Z by Z bar and plus I 2 alpha prime square root sum over n 1 over n e minus I n tau sine of n sigma. Okay. Now, P25, as before, is going to be quantized because we have a direction which is compact. So this term, this factor, this whole fact term, we can write it as plus 2 alpha n over r, and this thing becomes sigma because our z was e tau minus I sigma, then z bar is e tau plus I sigma. So if I take z by z bar, I will get e to the power minus 2I sigma. And if I take its log, I get a minus 2I. And that minus sign, the minus sign and I makes this, so we get, yeah, there's some small sign issue. I'm not going to worry about that, but essentially we get something like this. Okay. So now this is the string on the dual space, the 2T dual space. Now, the original string had Neumann boundary condition. So the original string had a Neumann boundary condition, which was this. At the end of the string, this is N stands for normal. But now, this thing becomes a Dirichlet boundary condition where this is basically saying that dt, T for tangent, so transverse, I think. Yeah. And x25, this x25 is equal to 0. Okay. So now we can say that what happens. So basically, if I T-dualize in an open string, what happens to the end of the string? So in the T-dual version, one end of the string is at pi, the other end of the string is at 0. So if I go back to this guy, we see that this is periodic. So this is not going to contribute. And then we see that this is also periodic. Not periodic, it's a constant, so that's also going to cancel out. What's going to contribute is this term. So sigma is going to change by pi. And there is 2 in front. So if I take the difference of the two string ends in the T-dual picture, I will get 2 pi alpha prime, and there's n by r from the quantization of the momentum. Okay? But now, remember that we are in the T-dual space-time. So in the T-dual space-time, the radius is not r, it's r prime. So if I express it in terms of r prime, I get 2 pi n r prime. So which means that the endpoint of the strings in the T-dual picture are separated by this amount. Okay. So what does this mean? So this means that in the original picture, this n was related to the quantization of the momentum. But in the T-dual picture, what it is saying is that in the T-dual picture, we have a space which is a circle, but I'm going to unfurl the circle and draw it as a line segment. And this is 0, and this is 2 pi r prime. And then what we have is that we have a string which starts from some point on this hyperplane. So the string, this point, it starts and it's going around. And as it goes to the end of the circle, it then comes around and it ends on the same plane, right? If it winds around more than once, then it can just, go and do the same thing again. Go and do the same. It can go through the hyperplane and then come, but it must end on this hyperplane. And not only that, the direction, the boundary condition on this thing, this is known as the Dirichlet boundary condition. Which means that the string cannot really move in this direction, right? The endpoints cannot move in this direction. So this is basically, so by considering the T-duality of open string, we find that the strings on the T-dual picture are bound on a hyperplane on which, they have a direction, their boundary condition is a Dirichlet boundary condition, right? So they have Dirichlet boundary condition in this direction, but they still have Neumann boundary conditions in this direction. So the strings can still move about in this direction, but they can't move about in this direction. So we see that there is a 24-dimensional hyperplane on which the string's endpoint is attached. So this is what we call a D24 brane, where D stands for, so D24 brane, where D stands for Dirichlet. So this is how we get a D brane. So a D brane is something that we get from considering how open strings behave under T duality. Okay. So I think let's just take a pause here and see if there are questions, and then we'll move forward.
I think I'm not fully sure how we got the Dirichlet boundary condition. Like, was that the thing we got by dualizing the Neumann boundary condition we used to have, or?
Right. So yeah, that's a very good question. So let me give a different way of thinking about it. Maybe it'll be clearer. Right. Right. So so the Neumann boundary condition. So the normal derivative, right? Let me just say it's the normal derivative of x25, right? So this is going to be del by del z of x25 by z. So this thing can be dependent on z bar. But here, even if there's z bar, that doesn't matter. It just drops off, right? Because we are taking the derivative with respect to z. And then we have del of x 25 z bar del of z bar. Okay. So that's basically something you can work out just from the definition of z and z bar and how they're related to tau and sigma. So the Neumann boundary condition is when we say that, you know, on the when we say that on the boundary of the string, this is 0, right? So this is what we have. Now, what happens is, on the other hand, if I look at the tangential, I think it is tangential. I was just saying transverse, right? Yeah. So, okay. Now, if I do T duality, what's going to happen is that under T duality, one of these guys will pick up a minus sign. So when it picks up a minus sign, it basically becomes this becomes x prime, and this is basically the I think it's just one second. Yeah. So you like this thing, you can basically say this is delta sigma of delta x, but this is going to be delta tau. Okay, so um, okay, so this is a mm, so basically, one way of seeing this is that um, the endpoints of the string, um, which appears at sigma equals to 0 and sigma equals to, say, pi. Uh, um, mm, just one second. I mean, it's kind of clear that these two things switch places, but it's just that I'm a little confused on how to show that this means that um, just one second.
Yeah, I think the rough idea makes sense now.
Yeah, it's just that, as you reach the boundary of the string, as you reach the boundary of the string at 0 or pi, if you go beyond 0 or pi, then you basically go off the string, right? So that means that the string is not, in that direction, x25 is fixed at the end. Okay, that's what it means. So that means that in that direction, it is, it doesn't, the string doesn't have um, any um, any movement, right? So yeah, so yeah, it's clear now for me. So let me explain what I'm trying to say. So what is this? Is t, right? Tau. So that means that this was the original boundary condition, right? Which meant that at the end of the string there is no momentum falling off, and then it becomes this thing at the boundary which means that the string is not vibrating in that direction at the boundary. Okay. Okay, because tau is the time, right?
Yeah.
So there is no, when you reach the end of the string, it's not moving in that direction. And that's why it's a Dirichlet boundary condition. Okay. So sorry for getting it confused. Is that clear?
Yeah, I think so. Thank you.
Okay. Thank you for the question. It's an awesome question. All right. So we now have a D-brane, and now if I go back to my original space-time and I now use a string which has a Chan pattern factor, then I can now ask what happens when I T-dualize and under the, what happens to this. So suppose that our Chan pattern factor, the gauge configuration, was just a diagonal of theta 1, theta 2 dot dot, theta n by 2 pi r. So this is just the kind of what the gauge field is of the Chan pattern factors, right? There is no like space-time, interpretation to this. So this A25 can be written as minus a diagonal matrix lambda inverse, which is a UN matrix, derivative of lambda, and this is going to be a diagonal is going to be E I x25, the 25th direction, theta 1 by 2 pi r dot 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 EI x25 theta n by 2 pi r. Okay. So if I do this, then we get something. We get something like this. I think we are still missing a factor of 2 pi r. No, it's fine because the 2 pi is here, right? So then what we do is that, what if we now go around my x25 and once, okay. So then basically what will happen is that, just like in the case of a charged particle, that is moving around in a around a stern, a magnetic field in the Aronoff-Bohm effect, the wave functions will pick up these factors. The wave function for the diagonal, in our case, it'll be diagonal. The Chan pattern factors will pick up these phases. Okay. And so now what's going to happen is that before, if you had a if you had a particle in a compact direction, it had a momentum which was n over r. But now, if I take the particle around, then because our wave function will now pick up a factor of EIQ5, what will happen is that the momentum will now pick up this. And why is that? It's because if I look at the wave function of a particle, it's something like P dot X, and P was quantized. But when we go around in a electromagnetic potential around a compact direction, it picks up a phase which is of this form, and so this means that the momentum which previously had some quantization like this is now changed by this amount. Okay. So but now what we have is that we have n of these factors. So if you have n of these factors, then what will happen when we do this? When x25 changes to x25 plus 2 pi r, then each of these wave functions now pick up these things. So now if I look at what's going to happen, to the dual picture, okay, I have to a little bit think about it a little bit. Just Okay. How do I think about it? Okay. So, so the idea is that, as far as I can see, is that, we pick, say, two of these factors, and for those two factors, if I consider the change in P25, so it'll be, so this was a quantized, so, this quantization of the momentum is what led to the winding. But now we have this sort of theta I and then theta J factors. And what these guys do is that, what they're saying is that as you go around the circle, your momentum is no longer quantized, it is fractional. Right, so this is fractional. So now if you do for a pair of, say, theta I and theta J, if you do the T dual version of this, and you say, okay, I have theta 25, pi minus x25, 0, then before you were getting 2 pi n r prime. But now, because of these terms, you're going to get this extra, we can take one of them to be negative, this extra term. And so what is happening is that because of the way that we have chosen our channel pattern factors, if you go to the dual circle, which went from 0 to 2 pi r prime, then the position of the endpoints, which now have Dirichlet boundary condition, are now given by theta 1r, theta 2r, theta 3r, so on and so forth. So now we have hyperplanes in these positions. And what happens is that an open string can end from one of the hyperplanes and go and end on another hyperplane. And they can do this. So they can do this. Okay. So as a result, what we have is that we have ND24 branes. Okay. So the only thing that is, well, it is subtle and something that I haven't derived here is how. And what I'll do is that I'll try to maybe fill in the gaps in the next class about how this formula comes about when you have these things. Okay. So it's actually kind of, I don't think it's very difficult. What you have to do is you start with the original x25, and then in the original X35, you had a term where you had a P25, right? So in that P25, you write N by R, and you essentially write this thing plus theta I by 2 pi R, right? And then this was, yeah. And then, yeah, exactly. So this is basically what you had in your original, I think that's how you do it, your original X25. And when you T dualize, everything else drops out. Everything, I mean, this cancels out, and the I think there's a 2 pi. So yeah, I'm kind of forgetting exactly how this is going to come out, but maybe you can try this, and we can fill in the gaps in the next class, okay? So what I'm trying to say is, if we go up to the this formula, right? And here, we have P25, and so what we did here was that we said, okay, P25 had to be like this, but in the previous thing, and that's what. But as we now go around the circle in the original space-time, the P25 now changes by this factor, by this term, which is over here, And once this has changed, if I now take this and then do a T duality, what will happen is that this and this will now cancel, and then yeah, we basically will get this guy. And now if I do x going to x plus 2 pi r, and then this thing will cancel from x pi and x0. And this will also cancel, this will be 0 because of the fact that we have a theta here. And we'll have, from here, we'll get sigma, and sigma will give me pi. And because in the change in the quantization of the string, in the quantization of the P25 direction, we had 2 pi here. So those pi will cancel over here. And so we will basically have something like this. Okay. So I think, yeah, that's the rough logic. I haven't really worked this out, but that's how you do it. Okay. So are there any questions?
No, I guess go ahead.
Yeah. Anyway, so sorry for the confusion, but this is basically um, the rough outline of how this works. Okay. So now, there's nothing stopping us from taking more compact direction. So we can take more compact directions and T-dualize them. So as we T-dualize them, the open string Neumann boundary condition in those directions will become Dirichlet boundary conditions. And therefore, if you take, if you dualize, say, if D is the dimension of my space-time, which is 26, minus 1 for the time, and P, so if I dualize this number of directions, right, then I will get p-dimensional hyperplanes, p-dimensional hyperplanes with Dirichlet boundary conditions, and they will be known as DP branes. Okay. And of course, you can do all kinds of rotations and all kinds of good stuff on those now. But that's not something that we have scope for in these lectures. One thing I wanted to say is that what happens when we take all the Chan pattern factors, all these to be equal? Then basically, obviously, what's going to happen is that the coordinate for all these D branes are going to coincide, and we'll have n D branes coincident. Now, intuitively, when we have open strings stretching between D branes, there will be some tension to these strings. So they won't correspond to any massless modes. But when these D branes are on top of each other, these strings will actually they will not have any masses. So we see that in the limit, of all the D branes being coincident, we have, say, new massless modes. And this basically is saying that the U1 to the power n symmetry will become then enhanced to UN symmetry. Right. So this is how we get UN symmetry, UN gauge symmetry in string theory via D branes. Okay. So this is all I have as far as D branes are concerned. I want to kind of come back tomorrow and give you the dimension, the word volume action of D brane. But for the rest of the 15 or so minutes that I've left today, I want to tell you a little bit about how fermions enter string theory, okay?
Yeah, in fact, I wanted to clarify this also. I'm forgetting if Shajid did that or not. That like right now we are doing purely like bosonic strings,
Exactly.
right?
So the
So
bosonic strings
this is
are
the
good
first
for,
time, like,
yeah,
this is the
yeah,
first time you are going to introduce fermions.
yeah. So bosonic strings are good for understanding the basics in detail. As you can see, the details themselves are a bit tricky
Yes.
and subtle. They're not very hard, but they're definitely subtle.
Yes.
So once you've understood the bosonic strings, the fermionic strings kind of follow the same kind of logic with a few more, quite a few more new creases. But so I won't be able to do, given the time constraint and my schedule, I won't be able to do the fermionic string in detail, but I can give you an outline. Okay.
Okay.
All right. So it turns out, so before we do the fermionic string, let me just do the fermionic string. I'm kind of, I prepared a smattering of topics, and I'm just like picking. You can see that I'm not very organized because I'm picking up stuff.
No, that's okay.
Like deciding what to do. And okay. So to include fermions in space-time, because what we want to do, we want to include fermions in space-time. That is the target space. But to do that, we need to introduce fermions on the world sheet. So there's a extension of the Polyakov action where there is fermions on the world sheet. So let's write the Polyakov action in the conformal gauge. So we fix the metric on the world sheet to be flat, so eta AB. So we still haven't fixed the whole gauge. We can still have a while invariance, while scaling. And this is, we have the background space-time is Minkowski. So this is, and then we have fermions, but these fermions are world sheets fermions, but they have a space-time index, which you can think of them as labels. And then we have the two-dimensional gamma matrix contracted with the flat derivative. So this is this guy and this guy. This is the massless Dirac operator. So this very simple action turns out to be supersymmetric. In fact, I think supersymmetry, although people didn't really realize that it was a string theory action, not this one, but the previous one that people did before Polyakov. That was where supersymmetry was first introduced in physics. Anyway, then for the two dimensions, the two-dimensional gamma matrices, there are many choices, but this is not that it matters, but let me give you a choice of the gamma matrices. So this is this, and it turns out that these spinors, of course, these are two-dimensional in the world sheet. So if we choose, light cone coordinates, then it's plus and minus. So these spinors or these fermions are Majorana fermions. Okay. And that has to do with the fact that these fields, these are world sheet scalar fields, but they represent the space-time coordinates. They are real. If they were complex, then we'd have to choose Weyl fermions. So these are the Majorana fermions, and if you look at the fermionic action in the light cone coordinates, it takes this form. the gamma matrices are absorbed in the representation. So if you multiply everything, this is what you. And of course, the equations of motions for this are very simple because we're in 2 dimensions. And we are in light cone. These are the equations of motion. Okay. Now, just as in closed strings, you can the bosonic strings, you can then now do a mode expansion of these things. But there are 2 kinds of boundary conditions that you can give to your closed strings, fermions on a closed string. So there are 2 kinds of boundary condition. Because they're fermions, as you know, it's kind of related to how fermions can pick up a sign under rotation. The first kind of boundary condition we are going to call the Ramond boundary condition. The Ramond boundary condition says that if you start at one end of the string with psi plus, as you go to the other end, it becomes psi minus. This is very dependent on the light cone. If you didn't have light cone, this would change its form. But I just didn't have time to do a more general thing. So this is one end. So in one end, this is basically, the 2 are the same. And when you go to the other end, and I'm using pi here for the other end, you get a plus sign. Okay, so this is the Ramond boundary condition. And there's another one called Neveu-Schwarz. So the Neveu-Schwarz boundary condition, it starts with the same on one end, but on the other end, we introduce a minus sign. Okay. So these signs change depending on whether you're using light cone coordinates or not. Minus sign. Okay. And the mode expansions depend on what kind of boundary conditions you use. And the Ramond boundary condition, the mode expansion becomes, you have some factor due to normalization, and it actually is the modes take integer values, and the mode operators or the mode coefficients, which will become operator upon quantization, we write D. And for the Neveu-Schwarz, so these are the analog of the worldsheet expansion, mode expansion for the bosonic string. This is much easier for the fermionic string. But here, because of this minus sign, the coefficients take half integral values, like, yeah. Okay. And then what you want to do is that you want to do some sort of quantization, something like this. Once you do the quantization and you go to the mode space, the Ramond sector becomes like this. Whereas the Neveu-Schwarz sector becomes like this. So if you take the Ramon sector, then you find something interesting. You find that if you look at this thing, it turns out, although I don't think I'll be doing this, this can be interpreted as in the Dirac algebra in space-time. Okay. And so this is kind of the Dirac algebra in space-time. There's more to the story. And therefore, to say create a space-time say spin half mode, one has to use the Ramon sector operators. Maybe I can, this is not very obvious from what I'm saying. Let me see how I can. I think it has to do with if you have a okay. I'm not going to worry about it right now. Maybe. So now it's still very, very mysterious how the fermions arise. So it's a bit of an involved calculation, but you can ask what are the massless modes? What are the massless modes of superstring theory? And quite interestingly, the massless modes don't really involve the bosonic operators. So there are two types of massless modes. One is called type 2A, in which you apply the Neveu-Schwarz operator an even number of times on the left movers, and the Neveu-Schwarz operator even number of times on the right movers. Okay, so this means it's a left mover, it's a right mover, and this means even, this means even. And then you can say R plus NS plus. Now these are going to be fermions. space-time fermions, and they will be gravitinos. Gravitinos. Okay. And then there will be NS plus, R minus, and they are also going to be fermions. And then there will be R plus, and these are going to be higher form gauge, abelian gauge fields. So what are higher form abelian gauge fields? Essentially, you know how A mu gives rise to F mu nu, and in string theory we have B mu nu, which gives rise to H mu nu rho. What these things are, they are like that, but they are C mu nu rho, stuff like that. So from which you can get, say, if this is a 3-form, you can get a 4-form field strength, but still abelian from here. And this will have a gauge freedom where if you replace C3 by an exterior derivative of a 2-form, then F4 remains invariant. And it turns out that these Ramon fields, these are the ones which are important for D-branes in superstring theory. So this is basically, let me finish over here. These guys give rise to the metric tensor G mu nu, the Cal-Bramon field B mu nu, and the dilaton. So in the superstring theory, it's really from the fermionic operators on the Rohr sheet that we get the massless bosonic fields. Okay, so this is kind of a bit of a surprising thing. So that was the type 1. There's another set of combination of operators that give us what is known as type 2 theory. The Neveu-Schwarz sector, NS-NS sector is the same, but the Ramon sector, these are slightly different. So this is the same as before, but over here, we have Neveu-Schwarz Ramon minus, Ramon plus. If you go back, here we had Ramon minus, and here we have Ramon. We had minus here and we had plus here. But now we have both of these pluses. And then we have, as before, R plus. Because both of these give rise to fermions. The fact that the signs here are different gives rise to the fact that type 2A is a non-chiral theory, meaning that it has both left-moving and right-moving massless fermions. However, type 2B turns out to be a chiral theory. That means that from the space-time point of view, it has only left-moving fermions. Of course, their antiparticle version is going to be right-moving, but there is a handedness, defined inside. So I'm just going to take 5 more minutes, if that's okay.
Yes, please.
So I want to kind of discuss what these Ramon fields do. So in type 2A, it turns out that we have D branes, which are where the value of D is even. So we have D0 branes, 2 branes, 4 branes, 6 branes, 8 branes. And in type 2b, one has 1 brane. There's something called a D instanton, which you can think of as D minus 1 brane. And then there's a 3 brane, 5, and 7, and 9 brane. So the 9 brane is interesting. It's a space-filling brane. So all of space-time, it fills space-time. So it's kind of the space-time itself. Because in string theory, in supersymmetric strings, the critical dimension is 10, not 26. Now, these things go hand in hand with Ramon fields. And in type 2A theory, these field strengths are even dimensional. So we have F true and F4. So, and do we have more? Let me see. So, and we have, yeah. So let's start with how a particle couples to a gauge field. So if you remember, a particle, which is an electric charge, as it moves through space, suppose the space has some electromagnetic field, the way it interacts with the electromagnetic field is through an interaction Lagrangian, where it's the charge of the particle times the A mu, the field, the gauge field, and its world line, right? So so this is, say, I don't know, gamma, you integrate over this, right? This is going to be the interaction term. And and the way that we determine the charge of a particle is that we surround it by a sphere, and S2, and we say, okay, there is some electromagnetic field going through the sphere, and we integrate this electromagnetic field on this sphere. This is what we call the total. It gives me the total charge inside, right? So the point I'm trying to make is that a zero-dimensional particle, when it moves through space-time, it has a one-dimensional path. And because it has a one-dimensional path, it couples to a one-dimensional vector potential. And a one-dimensional vector potential, when you take its exterior derivative, you get a two-dimensional field strength. Okay. Therefore, when you have a D0 brane in your theory, it is natural to have a two-form potential, right? In the same way, a charged particle couples to the two-form Maxwell potential, Maxwell field strength. So this is a two-form field, not a potential. Similarly, if you have a D2 brane, the D2 brane, as it sweeps out, so maybe it's a two-dimensional surface, it sweeps out a three-dimensional surface. And therefore, you have some C mu nu rho, D of X mu, wedge D of X mu, D of X rho. This is the coupling of this object. But how do you measure the charge of the D2 brane? Well, if this is a D2 brane, you have 10-dimensional space-time, and then you subtract one dimension because of time, so you end up with 9-dimensional space-time. And then you say, okay, my D2 brane has 2 dimensions, so we have 7 dimensions, which are yeah, we have 7 orthogonal direction, right? So of this 7 orthogonal direction, if you take one of this direction to be the radial coordinate, then you have 6 direction left. So to sorry, I am I'm obviously making a mistake. So it sweeps out this thing. The D2 brane is going to give me okay. So you see that we have a 6 dimension to measure the charge of the D2 brane. We have to surround it with an S6, right? So I must have made a mistake, because the thing that you can naturally integrate on an S6 is going to be a 6 form. But a 6 form okay, sorry, I made a mistake. Let me just go back and fix it. Sorry, I haven't done this for a while, so I've forgotten my geometry, my higher dimensional geometry. So let me just figure this out. So the particle one is fine, but what happens if I take a string, then the string sweeps out 2 dimensions. So we have a 2-form potential. And so then what we do is that we get a 3-form potential from from B2. Okay. And right. So okay, let me just, so the string is the string is one-dimensional. So we surround it by a circle. Mm. Yeah, I've kind of forgotten this geometry. I'm sorry. Let me just remind myself this and come back and give you um, how to use these sort of NS the Ramond sector, how to use that to quantize the D brane. So I'm very sorry, I just don't remember that part. I'll tell you about it tomorrow. Is that all right?
Yeah, it's perfect. I mean, it gives a glimpse to the participants that, the learning curve of string theory is very, demands a lot of background and
Yeah, the learning curve of string theory is very steep,
yeah.
but the forgetting curve of string theory is also very steep. So, I mean, I used to know this like the back of my hand, but of course, I haven't done this for a while because I don't do string theory. I haven't done string theory for a number of years. I have forgotten some of the details. Okay, so
No, but
and
it was very clear. All your lectures have been very clear, and I hope they have helped the participants as much they have helped me.
yeah, I mean, I like to be honest, I really like making mistakes in class because I I I want my students to see that it's okay to make mistakes. Because yeah, anyway, so I'll come back tomorrow and I will finish this off, and I will also introduce I will also give you a good argument for why the Ramon sector gives rise to space-time fermions, and then I'll finish off with a argument about how to derive the space-time action of string theory. Okay.
All right. Perfect. Perfect.
Okay. All right. So I'll see you guys tomorrow. I don't know